Unit 2, gram stoichiometry. We're going to start off with the front page of some review of some of the things we did earlier this week. So the first question is just asking you to balance this equation. So we're going to do it the traditional way. That's kind of what you want to eventually go to. So in the middle, you just write down your elements and count what you have on each side. Three oxygen, 3 oxygen. So oxygen's already in balance, although that might go out of balance temporarily as we solve the problem. So easiest thing, it looks like the balance is carbon. Again, you want to stay away from oxygen because it's all over the place. Save it for last. So we're going to start with carbon. So there's 3 carbon here. So 3 carbon balances with 3 carbon. In doing that, so I want to change my carbon number here. Go ahead and keep track as you go along. In doing that, I changed oxygen. I now have 3 times 2 is 6, plus 1 more is 7. All right, now let's do hydrogen. You have 6 on this side, 2 on this side. So if I multiply this by 3, that'll put the hydrogen in balance. 3 times 2 is 6. And 6 on this side. So hydrogen is in balance. Carbon is, oops, what did I write there? That should be a 3. Okay, that should have been a 3. Hope you were wondering what that was. I don't know what it was either. Okay, so there you go. All right, so carbon, hydrogen are in balance. When you did this, you added one of those. So now you have 7 and 3. It's a little bit of an odd number. Excuse me, I take that back. You have 3 times 1 is 3, and 3 times 2 is 6. So 3 times 2 is 6, 3 times 1 is 3, that puts you at 9. Okay, there we go. Now, on this side, how many do you have? You have 1 and 2. So you have 1 here. You need to get to 9. You already have 1 here. How many more do you need here? You need 8 more here. So 1 plus 8 would give you 9, would balance it. So what do you need to turn that into an 8? You need a 4 up there. Remember, coefficients are always multiplying. So now I have 9 there. So everything looks like it's in balance. Let's just check. C3 and 3C balance. H6 and 3 times 2 is H6. And over here is 1 oxygen. 8 oxygen is 9. Over here is 6 oxygen and 3 oxygen is 9. So everything's in balance. So you can put a 1 there if you want. So it's 1, 4, 3, 3. All right, next one is some stoichiometry from Wednesday, just regular gram stoichiometry. So I gave you a little room to draw a graphic organizer if you would like to do that. So up on top we have moles. This is the chemical world. And we're going to draw some little boxes here. In the world of moles. And if you're so inclined, you can draw a light little box around. That's chemical world. That's a different world from us. Out here is our world, and that's grams. All right, and it's down here. And in between the two, we need the translators. So that would be the molar mass. So for water, it's 18.02 grams. Okay, for KOH, let's figure that one out. Potassium is 39.1, oxygen is 16, and H is 1.01, so we're going to add those. And that gives us, oops, made a mistake. $56.11. And for K2O, it's going to be, now we may not need all of these, but let's go ahead and put them in anyway. So K is 39.1, we just said that. You multiply that by 2, and then you add 16 for oxygen, and that gives you 94.2. So now you have a way to translate between moles to grams or grams to moles. All right, let's go ahead and get started with the first problem here. How many moles of KOH? So let's find that. It's in the moles row and it's KOH, so put a light question mark there. Are produced from 4.12 grams of K2O. So grams is out here in our world. It's something that we weighed. So we have 4.12. All right, so what's the strategy? We need to go through the molar mass to get into the equation for K2O, and then we need to go across the equation to get KOH, get moles of KOH. So that's a two-step process. 1, 2. So we start with what we know, way over here. And we use the molar mass. You make your two ratios. Hopefully by now you're getting to where you can do those in your head, and you can see that you need to put one of these over the other and then reverse it, put the other over the top, and you can see that grams of K2O have to appear on the bottom. Okay, so now we're sitting in this box right here of moles of K2O. Now we need to move across to moles of KOH, but I didn't balance my equation. I did that on purpose because I wanted to see that you understand you've got to do that. So let's see. Let's start with K. K looks pretty easy. There's 2 there, 1 there, so I'm going to put a 2 here. So I have 2K, 2K. Now that doubled my oxygen there. So I have 2 oxygens, and I have 2 oxygens on that side. It also doubled the hydrogen, so now I have 2 hydrogen, and I already had 2 hydrogen on that side. So everything's good. So my coefficients are 1, 1, 2. All right? So now what we're going to do is we're ready to move across here. So we need moles of K2O to cancel out, and our final answer, I didn't write it down here, but let's go ahead and do that. We need the last man standing to be moles of KOH way down here. So this last conversion has to make moles of K2O cancel out and moles of KOH appear on the top. So we have 2 moles of KOH on the top. It should be moles of KOH. That I didn't do on purpose. Okay, and on the bottom I need moles of K2O. There's 1 of those. Okay, so let's do the cancellation. I didn't do this one. Grams of K2O with grams of K2O there. Moles of K2O with moles of K2O there. Last man standing is mole of KOH. So I'm going to multiply 4.12 times 1 times 2 divided by 94.2 divided by 1. And that gives us 0.87. We can go to 3 significant figures because those are okay. So it's actually 0.087. See, significant figures aren't hard. Most of the time you're doing significant figures, it's multiplications and divisions, and they're pretty straightforward. It's just what is the number out here that has the least number of significant figures. That's how many you can use there. So it's really not as complicated most of the time as it might have seemed when you were learning it back a few weeks back. Okay. It's out of the light here. Okay, next one. Let me erase my graphic organizer here. Okay, how many grams of H2O? So I'm going to be down here in grams of H2O. That's a how many. That's what I'm trying to find out. Will produce 6.37 grams of KOH. So that's 6.37 there. So again, my chemical equation is flowing from left to right, but my math equation is going from here, up to here, over to here, and down to here. So I start on the left side with this, what I know. So, and this is going to be 3 conversions. I'm going to start way over to the left. Okay, first conversion. Again, I'm not going to write down all the ratios. You kind of start to get to where you can do this in your head. I need grams of KOH to cancel out. So right there, grams is going to have to be on the bottom. So grams cancels with grams of KOH. All right, now I'm up here sitting in this box. I need to come over to here. I have a 2-to-1 relationship between KOH, moles of KOH, and moles of H2O. I need moles of KOH to disappear, so it's going to go on the bottom. Moles of KOH cancels with moles of KOH. Now I'm sitting in this box right here, and I'm ready to come out for the final answer using the molar mass of water. So I need moles of water to cancel out, and my final answer, I never did write that, is grams of water. Okay, so right here, I'm going to need moles of water. I'm going to use the molar mass here. I need moles of water on the bottom. And I need grams of water to be on top to be the last man standing. That's grams of H2O, which is going to be there. So moles of H2O cancels. And so it's 6.37 times 1 times 1 times 18.02 divided by 56.11 divided by 2, and that'll give us our answer. And that gives us 1.022, and we can go to 3 significant figures because of that, so we're going to call that 1.02. All right, there's our answer right there. Okay, last one. And these are review of Wednesday's stoichiometry. So this is stoichiometry. It's how you work your way in and out of a chemical equation. That's what stoichiometry is. Okay, how many grams? Let's erase a graphic organizer. How many grams of K2O, so that's going to put us right here, and they're asking how many, so that's our question mark, will produce 2.3 moles of KOH. The 2.3 is going to go over here. Oh, moles, not grams. Got to read the question. So it's up here. Okay, so how many grams? Let's just double check that we did it right. How many grams of K2O will produce 2.3 moles of KOH? Okay, so chemical equation is flowing to the right, but our math equation starts with what we know. We come across the equation, moles to moles, and then we come out using the molar mass of K2O. All right. So what it's asking for is grams. And what we start with way over here is 2.3 moles. And it's a 2 conversion problem, 1, 2. So the first one is moles to moles. So there's 2 moles of KOH for every 1 mole of K2O. I need moles of KOH to cancel out, so that's got to be on the bottom. And I need 1 mole of K2O on the top. Moles of KOH cancels with moles of KOH. Okay, now the last conversion's coming out using the molar mass. I need moles of K2O to cancel, so that mole is going to be on the bottom, and the grams is going to be the last man standing on the top. Moles of K2O, last man standing right there. So it's 2.3 times 1 times 94.2 divided by 2 divided by 1. And I get 108.33 grams. But we're limited to 2 significant figures. Okay, so I'm going to put down that number here. But if I'm limited to 2 significant figures, what's that going to be? It's going to have to be 110. That's the 2 significant figures with no decimal point there. Okay? All right, so that takes care of the review problems. Now let's get into limiting reactants. Okay, so if you watch the video, these aren't too hard. You have to run the reaction twice. Once where you've used up all the CH4 and once where you've used up all the O2. And then you see which one of those reactions causes its reactant to run out. First thing we have to do is we have to compute the number of moles. But it's already done for us here. So this problem, it was given to you in moles. And this should say, it doesn't say, it should say moles. So that means we don't have to do the molar mass conversion. So we're ready to go. So we're given, and it ultimately asks us at the end how many moles of CO2, but let's take care of that later. We have 5.1 moles of CH4 and 8.7 moles of O2. So in the CH4 column, for all CH4, we're going to use all 5.1 of those moles right there. Okay, and we do a little bit different order than the video. I'm just going to go ahead and fill this in. In the oxygen column under all O2, I'm going to put the total number of moles we were given for O2 right there. I'm going to go ahead and fill that in right away. Okay, so these are the things that we were actually given. We have this much CH4, we have this much O2. Now what you have to do is figure out the relationship. Again, I like to write coefficients in front of the coefficients of 1. So you have a relationship of twice as much oxygen as CH4. You need 2 moles of oxygen for every 1 mole of CH4. So that means if I'm going to completely combust this, I'm going to have twice as many moles as this of the oxygen because it's 2 to 1. So I multiply that, I get 10.2. Okay, now for this one. Again, it's a 2 to 1 ratio. I'm going to need twice as much oxygen as I have CH4. So in order, now we're talking about what does it take to burn all of the O2. It would take half this many moles. So it's 8.7 divided by 2. And that gives us 4.35. So what you want to look for at the end, is there a ratio? Are these ratios the same as this? 2 to 1. This number's twice as big as this number. This number's twice as big as this number. This number's twice as big as that number. That's what you want to look for at the end to see if you did it right. Okay, so now we're going to go around this and we're going to see, do we have at least this much of each of these compounds? And we're going to just put a yes or no. You can just write Y or N if you would like. I'm going to do that. So do we have at least 5.1 moles of CH4? Yeah, right there. We were given 5.1 moles of CH4, so I'm going to put a Y there. Okay. Do we have at least, in order to burn all of that, you need to have 10.2 moles of O2. Do we have at least 10.2 moles of O2? Well, no. The answer is no. We were only given 8.7, so that's going to be a no. How about the O2? Let's check this reaction. Do we have at least 8.7 moles of O2? Yeah, we just answered that question. We have exactly that much. So that's at least means exactly that much. Finally, so if we want to burn all of this, we have to have this much CH4. Do we have at least 4.35 moles of CH4? Yes, we have 5.1 moles. So the answer is yes. I should have put a yes there and a yes there. So when you do these, you're always going to come out with 3 of the boxes with a yes and 1 with a no. All right. So that's how you do set it up. Now the limiting reactant is this one. The one that has the no in the column. So the column that has the no is the limiting. So I'm going to write this shorthand. I'd like you to write full sentences. It's O2. O2, and I'll write a short sentence, is limiting. Okay. How much of the non-limiting reactant is in excess? Well, the non-limiting, this is the excess. The other one is always the excess. Okay, so first of all, we have to identify which reaction is going to work, which one actually runs. It's the second one. Here's why. Think about this. In the first reaction, you wanted to burn all of the CH4. But that would have required 10.2 moles of O2. You did not have that many moles. You only had 8.7. So your O2 ran out before you could burn all of that. So that reaction could not run to completion. Down here in the second reaction, you wanted to burn all the moles you have of O2, which is 8.7. In order to do that, you needed 4.35 moles of CH4. And that was fine. You had 4.35 moles of CH4. You had more than that. You had 5.1. So this reaction, I could burn the oxygen all the way through, all of it. I could not burn all of the CH4. I didn't have enough oxygen. So it's always one is limiting, one's excess. So what's the excess? It's simply the difference between these two numbers. It's always a positive number, of course. So it's going to be 5.1. That's how much we were given of the CH4, minus the amount we actually had to use to burn all of our oxygen. We didn't need any more than that to burn all of our oxygen, and that was 0.75. So the non-limiting or excess reactant is 0.75 moles, and we should identify it. It's CH4. So we have 0.75 moles of CH4 left over. And the chemistry term for that is in excess. Okay? I'm in the light. Try to stay out of it here. Okay, next up is how many moles of CO2 and H2O are produced. So this is pretty easy. How many moles of CO2? Well, look at our balanced equation. 1, 2, 1, 2. So I'm going to have, if this reaction, let's identify the reaction it's going to burn. It's this one, the one that's going to, I should read. It is burning, but it's the reaction that's going to run. So it's the bottom one. It's the one with the 2 yeses in it. That's the one that's actually going to react. You can actually burn up all of your oxygen and not run out of your CH4. Okay, so the question is, how many moles of CO2 do we end up with? So we're not interested in what you can do in effect. I should point this out. You can draw a line through that. You don't need that anymore. Okay, so I have 1 mole of CO2. I have 1 mole of CH4. So in this particular reaction, 1 mole represents 4.35 moles. So if it's 1 to 1, that means this is going to be 4.35 moles. All right, and for water, it's 2 H2O for 2 O2. So that's a 1-to-1 relationship. Okay, 2 to 2 is 1 to 1. It means it's the same number, in other words, right? That's the same number as that. So if I have 8.7 there, I have 8.7 there. Okay, and that's how many you would get. So you're going to be able to produce 4.35 CO2 and 8.7 okay, there that is, and I'm out off the screen. I'm sorry. Okay, so in this one I do give it to you in grams. You have 5.82 grams of C2H4, so let's convert that to moles. We have to be in moles. See if I can squeeze it in right here. Actually, I want to use that space later. I'm going to do it up on the top. Sometimes you just have to find your space. And that's true on the AP or any standardized test sometimes. You may have some nice method for solving something, but they don't give you any space on the test. So you got to kind of figure out how to squeeze that in. So I'm going to put it up here. So for C2H4 ethylene, a molar mass of ethylene. You have 2 carbons, that's 2 times 12.01 is 24.02, and you have 4 hydrogens at 1.01 each, that's 4.04, so that's going to give you 28.06. And that's 0.207. We have 3 sig figs there, we'll go for that. Leave myself a lot of space. I'm going to have to go up above here. Okay, so for 8.9 grams of O2, and O2 is 1 mole is 32. It's 2 times 16. Okay, 8.9 divided by 32 is what it turns out to be. And that's 0.278. Okay, so these are the numbers we're interested in. So this is how many moles of O2 we were given. This is how many moles of C2H4 we were given. So let's put them in the boxes down here. If I want to burn all of the, and I didn't change this, it should be, I just left the 2 out there. Yeah, if I want to burn all of the C2H4, that would be this much, 0.207. So I'm going to put that here. And if I want to burn all of the O2, 0.278, I put that here. It's in the oxygen column, and it's under all O2. Okay, so what kind of relationship do we have? We need 3 times as many moles of O2 as we have moles of C2H4. So you're going to take this number and multiply it by 3. That's how much oxygen it would take to combust all of the C2H4 that we were given. So you multiply 0.207 times 3, and that gives you 0.621. Alright, this one you go in the other direction. You need 3 times as much oxygen as you have C2H4, so I divide this number by 3 to get that number. And that is going to be 0.093. So again, just check your work. This should be a 3-to-1 ratio for all 3 of these. 3 of these to 1 of these. 3 times as much of this as this. 3 times as much of this as this. So just double check and be sure that that's what you got. Okay, so the 2 that we know we have, and I usually do this, I taught students to do this, I didn't say it to you yet, is I circle the ones we know we have. Those are the ones we were given. That's what we calculated up there. So now we're going to go around and determine, do we have at least this much of each of these compounds? So for C2H4, if we're going to burn all of the C2H4, this would be a yes. That's how much we were given. So the ones that are circled, we know we were given that much. Okay, next one is O2. In order to burn that much C2H4, we need 3 times as much, or 6.621 moles of O2. Do we have that? The answer is no. We only have 0.278 moles of O2. You could also look down there and see it. That's all we have. So that's where our no is. We're just going to go ahead and continue though. We know we have this much. That's what we were given. That's a yes. And do we have at least 0.093 moles of C2H4? Yes, we have this much, 0.207. So that's a yes. So the no is over here in the O2 column. So that's the limiting reactant. You can just write it down here. That means the other one is the excess. It's the one that has 2 yeses in the column, yes and yes right there. So that means that C2H4 and how much? It's just the bigger number minus the smaller number. It's never a negative number. It's a real amount. It has to be a positive number. Kind of going off a little side there. So just do that on your calculator. And we get 0.114 moles of C2H4. So that's that. Okay, how many moles of CO2 and H2O? Okay, so now we're interested in moles of these. First of all, which reaction is going to run? You have to answer that first. It's the reaction that has yeses in both of the boxes in that row. So it's this one. It's the all O2 is going to run. Again, let's think about that for a second. We have this much O2. To burn that, to combust every bit of it, we need to have at least that much C2H4, and we do. So we can make that, we can use up all of our O2. It's possible for us to do that. With the C2H4, all C2H4, in order to burn all 0.27 moles of C2H4 we were given, we need that much oxygen. And we found we don't have that much oxygen. So this reaction cannot run. Just put a line through it if you like. The reaction on the bottom is the one that's going to run, the one that has yeses in both of the boxes. All right, so we're going to go ahead and figure out how many moles of CO2 do we have. Well, there's not a nice 1-to-1, 2-to-2 like there was in the last problem, but there's still easy enough relationships. So here you go. You know you're going to end up with 2 moles of CO2 for every 1 mole of C2H4 that you combusted. How many moles of C2H4 did you combust? This number. So this number, if this number is twice this number, then this number. All right, so we multiply 0.093 times 2, and we get 0.186. And we get 0.186, 0.186. Okay? All you have to do is find a relationship that's going to work. So that's a 2-to-1. Now, how many moles of H2O do we get? Well, here you see a 2-to-2. That's a 1-to-1 relationship. So you're going to end up with the same number of moles of H2O as you have of CO2. So that's also going to be 0.186. All right? And so that's how you get the moles. Now to get the grams, it's just a molar mass conversion, so let's just do that quickly. It's always good to practice those because they have to become very natural, and even to a point at some point where you want to kind of do them in your head. So for CO2, it's 44.01 grams of CO2 in a mole. So you multiply 0.186 times 44, 44.01, and that gives us 8.19 grams of CO2. Same thing for oxygen, same number of moles, but different molar mass. I said oxygen and then water. 18.02 grams per mole. Okay, and I cancel moles H2O, moles H2O. I should have done that up here with the carbon dioxide. Too late. Okay, 0.186 times 18.02, and that gives us 3.35 grams. And I'm not going to worry about significant figures here. Not CO2, H2O. Okay, 3.35 grams H2O. Okay, and I'm off screen. So there you go. So get that down right there. Again, same exact thing, except different molar mass for water than for carbon dioxide. So that takes care of all the assignments and solutions for this unit, Unit 2. And we're going to move into some more stoichiometry next week of gases and of solutions. Those are basically liquids. And so we'll get started on that. So this just get these assignments done. Try to do one a day. That's the goal. And we'll keep moving forward. Anyway, have a good day.